Good evening. My name is Leon Alkali from the Jet Propulsion Laboratory. It is a great pleasure of mine to introduce our next speaker, Dr. Steve Chen, who is a colleague from the Jet Propulsion Lab, but also a dear friend of mine. I'll read a very brief biography, and then you're in for a treat. The topic is artificial intelligence and space. So Dr. Steve Chen is head of the Artificial Intelligence Group and senior research scientist at JPL. He has led the deployment of AI software to a wide range of missions, including autonomous science craft on EO-1, Earth-observing sensor web, Watch on MER, the IPEX CubeSat, and decision support for science planning and automated data downlink on the ESA Rosetta orbiter. He is currently supporting the development of the onboard scheduler on the Mars 2020 rover mission, as well as mission analysis and scheduling technologies for the EcoStress and OCO3 missions. Beyond his individual contributions as he's the head of the Artificial Intelligence Group at JPL, and the list goes on and on and on, but I'll just introduce him as my friend, dear Dr. Steve Chen. Take it away.
Thank you very much, Leon. So it's a great honor to be here to talk to you a little bit about how artificial intelligence is influencing almost every aspect of the space enterprise. I'd like to start out first by thanking Bernard Foying, who suggested that I come to this conference and talk about artificial intelligence. And then second, start with a disclaimer. A lot of the examples of deployed AI systems that I'm going to be talking about, a lot of them are from JPL, and that's because there's quite a bit for me to cover, and it's easiest for me to talk about some of the examples that I know best. So to start out, AI in space got a tremendous boost in 2003. That's when we got the approval to upload artificial intelligence software called the Autonomous Science Craft to a spacecraft called Earth Observing 1. So Earth Observing 1 was a technology demonstration mission that flew two very important instrument technologies, the Hyperion Hyperspectral instrument and the Advanced Land Imager, which is the precursor to the OLI. So in many ways, EO-1 was a typical Earth observing satellite. It was able to point, it was able to observe. What was unique about what we were able to do with this spacecraft is give it artificial intelligence to enable it to analyze imagery on board and make subsequent decisions about its operation based on what it analyzed and saw. So it could analyze the images on board, see if they were cloudy. If they were cloudy, it could reject the image, plan to take another image of the same site on its own. Or it could do different kinds of science analysis. And what this video is showing is actually it overflying the Mount Etna volcano in Sicily, one of our common science targets, and analyzing the image to measure the thermal emissions. So it could do this on board, and it could decide whether or not that was a sufficiently interesting science activity with policies defined by the science team in a very natural language, allowing it to, say, retask or send down an alert and take action independently. And it did this thousands of times over a dozen years. IAC was able to operate this way. It originally was supposed to be a 6-month technology demonstration, but it performed so well that it operated for over a dozen years, acquired over 60,000 images, over 3 million commands issued, all under artificial intelligence control. And the primary benefit of this is that people could now interact with this spacecraft and in a much more natural way. Scores of institutions around the world could task, get different science results down directly from either the spacecraft or from different workflows, and actually construct operations policies themselves. They could actually task the spacecraft from anywhere they had an internet connection. In fact, there was a smartphone app at one point in time deployed by a contractor, so they could task the spacecraft, see the results of their tasking. What's better than one spacecraft controlled by AI? In fact, multiple spacecraft working together controlled by AI. So what this video is showing is one of our sensor web use cases where we track forest fires using the rapid-fire system, which processes MODIS data on the ground based on Terra and Aqua, and actually uses those detections to autonomously retask other satellites, including EO1. And this is the true test of the ability of your AI, that when it can take taskings not from a human, but from another software system, that's when we're really getting into the interesting stuff. So not only did we track forest fires with this, we actually tracked volcanoes worldwide. We had a network set up that involved multiple satellite systems, ModVolc, again, which uses MODIS, GOES-Volc, which uses the GOES satellites, the Air Force Weather Advisory, the Volcanic Ash Advisory Center, which is what's used by all the commercial aviation, as well as scores of individual volcano observatories linking in their ground sensors. And we use all of this information in order to best estimate active volcanic eruptions and monitor volcanoes worldwide. This system was so successful, we processed over 100,000 alerts, and for the imagery that we were able to acquire, over 35% of these images had an active thermal signature. That's about 100 times the background rate of volcanic emissions as measured by the baseline ModVolc system. So this is a much more efficient way to use our scarce satellite resources. We were also able to use the same kinds of techniques to track flooding. In a multi-year campaign in collaboration with the Hydro Agroinformatics Institute in Thailand, we actually used broad-scale, wide swath, low spatial resolution flood data to determine the key areas that are flooding. We used in situ data combined with that broad-scale information to feed flood and hydrological models and use that to task a range of different sensors, including a wide range of commercial sensors. This enabled us to double the temporal density of our water volumetric estimations, and this information could then be used by the Hydro Agroinformatics Institute for flood mitigations, as well as NGOs and other entities. So this was, again, a tremendous demonstration of the power when we harness multiple satellite systems and ground systems and modeling all working together. So now, let me tell you a little bit about some of the AI that we used. So all kinds of machine learning are fundamentally about forming different decision boundaries in our data sets. So this is actually showing, oops, let me get my pointer here. This is actually showing discrimination of clouds versus other parts of the data, and this is using an optimal Bayesian thresholding techniques. Depending on how aggressive or conservative you want to be, you can model this and have an aggressive classifier or a conservative classifier using different dimensions. And the beauty of machine learning is people have challenges dealing with high dimensional data sets, but the software and the math doesn't really care. So particularly if you have hyperspectral data, you're dealing with hundreds of dimensions, you can actually develop these classifiers very effectively. And this is a very efficient form of classifier that was used to deal with very large data streams on board the AVERS NG airborne instrument, and we later adapted it for use on board Earth Observing 1. But machine learning has a much longer history on board Earth Observing 1. Since 2005, we were using support vector machine learning techniques to track the growth and retreat of snow, water, ice, and land. This allows us to do not only flooding measurements, but actually track glacier growth and retreat and perform different kinds of cryosphere science. This technique was so effective, it actually outperformed the best available expert-derived, manually constructed decision trees for doing the same classification. So, and you can see in all my slides, I have citations for people who have more interest in a lot more of the details. So one of the ultimate tests of this was a technology demonstration we did to show that with machine learning, we could detect very subtle sulfur signatures at Bjorup Ford, which is in the extreme northern part of Canada here. And this is actually a sub-pixel detection here because Hyperion has 30 meter by 30 meter pixels, and this is pretty much a sub-part of 1 pixel that's definitely not even pure sulfur. This was actually chosen because this is the only known Arctic sulfur spring site, and this is considered an astrobiology analog to something that you might see on the surface of Europa if you were to have a similar system. So again, we can detect these very subtle signatures using this kind of machine learning technique that otherwise we wouldn't be able to do. And we're going to see this theme repeated again and again. Well, I said before that a lot of the machine learning techniques use decision trees. Another variant of this technique is called random decision forests. What you do is you actually learn multiple decision trees on the subsets of the data, and you compete them against each other and use them as an ensemble classifier. This is, in fact, the heart of the TextureCam system, which is designed to someday go on board a future rover to allow rovers to detect and classify different objects and use that to conduct their science. This is actually a flight showing the flight of this technique on the IPEX CubeSat, and you can see these are the different decision trees that are generated, and then we use them to compete against each other. We also use this technique on board the Earth Observing 1 mission. The most powerful onboard processing technique that we used thus far in space is hyperspectral and mixing. So our human eyes see things in roughly 3 spectra. The visible wavelengths, roughly speaking, red, green, and blue. But as many of you know, and probably many of you know much better than me, there are instruments that we can build that now can see things at 100 or even more than 100 spectral wavelengths. And the challenge is, how do we use this data, and how do we use this vast amount of data that we have on board the spacecraft? We actually put together a system that first does superpixel segmentation, that groups the portions of these images into large homogeneous regions, and then this drives down this improves our signal-to-noise ratio, and then we use this SMAC end-member extraction. This is a linear unmixing technique that figures out what are the individual spectral signals that I have that are most likely to compose the signal that I'm now seeing at the instrument. And this is showing that on board, in these 2 cases, we were able to reconstruct the benchmark ground analysis by Cruz and Grant with both Avarice and Hyperion, and to construct the same kind of approximate spectral unmixing. In other words, to determine what the individual mineral constituents are in this Cooperite, Nevada scene. This has a lot of tremendous applications in data reduction and also focused science. If we can, instead of bring down the whole data cube, search for specific spectral signatures and figure out what we're seeing and know what's expected and what's not, we can send down the most important science data intelligently. And that's going to be a continuing theme that I'm going to be harping on this entire talk. The other thing that I want to talk about is everybody talks about supervised machine learning. That's when you have particular classes, you know you want to detect them, and you train them using expert labeled data. The other thing that I want to make sure is not ignored is unsupervised learning. This is where you see the data and you figure out structurally that some parts of it are more interesting than other parts. And this is generally all some form of outlier analysis. This is showing a particular technique that's working in visual salience, that's looking at the visible color regime here. And this is a rural scene in Thailand, and this is a heat map over here. And the parts that pop here are actually buildings, and that's because color and albedo-wise, they're tremendously different. So if you took pictures of thousands of images of a rural countryside, this technique would say, hey, these buildings are quite interesting. And so they would pop, and so maybe you would downlink more images of them or tell somebody that that's what you saw. The other technique that you can do with artificial intelligence is you can effectively create new sensor types that are derivative from the original data. This is actually some work we did in analyzing volcanic images. This is commercial imagery from the fantastic WorldView 2 satellite. This is actually spectacular imagery of the Eyjafjallajökull volcano eruption in Iceland in 2010. Most of you probably remember this because it shut down air travel between North America and Europe and caused immense economic damages. What we do here is we stretch the image, and then we use the TextureCam classifier that I mentioned before with the random decision forest. And this is a classification map that says, here's the plume, here's the shadow, and the rest of this is land. Once we have that information, we can use that combined with geometric information. We know where the spacecraft is, we know where the sun is, we have a digital elevation map. We can now estimate the plume height automatically from that information. And what have we done now? We've taken a visible sensor and we've created a plume height derivative sensor. And that plume height derivative sensor, the scientists are very, very interested in because that's a proxy for the strength of the volcanic eruption. Just like thermal emissions are a proxy for the strength of the volcanic eruption. So we've taken a standard visible sensor and we've made a volcanic activity, emission strength sensor. So I talked a lot about interpretation of the data and machine learning. The other piece that I'm going to be talking a lot about today is on the response side. What do I now do with that information and how do I action that? And that's the other side of artificial intelligence, which I'll call model-based AI. And in this system, in this approach, you use a model of the spacecraft, a model of the operations, and you automatically derive things like this, a schedule, by knowing the impacts of all of the activities that you're doing on the overall state of the spacecraft. What does this mean? This means that we have to know when we do a calibration for this particular instrument, it really means do these other activities. We need to know things like, where is the spacecraft? How long does it take to slew? How many times can it slew consecutively? How does the momentum build up? How do I deal with the built-up momentum? I need to know things like, when I turn the instrument on and off like this, the instrument temperature is going to go higher and higher, and I can't allow the instrument to overheat. So eventually I need to stop and turn the instrument off and let it cool. So all of these things together allow the spacecraft to take high-level goal requests, in other words, image requests and priorities, and manage all of its own resources for itself, which is particularly important when you're talking about larger and larger numbers of spacecraft. So unfortunately for us, Earth Observing 1 ran out of fuel, and so in spring of 2017, the satellite was decommissioned. However, you don't need to feel sorry for us because there's many other future things that we've worked on. To start with, we're very proud of software that we have on board both of NASA's rovers that we have at Mars right now, both the Opportunity MER rover and the Curiosity MSL rover. And this is automated targeting software that uses artificial intelligence most strongly with the ChemCam instrument, which is a laser-induced breakdown spectrometer. What this instrument does is it has a laser, it can fire at the rock, can get spectral measurements of the underlying rock because we don't want to measure the same red dust over and over again. And this is one of the important science components for the MSL mission. Well, before the Aegis software was uploaded, they had to do all of that manually. What does that mean? At the end of a Martian sol, they would take a panorama image or a wide field of view image. They would manually select a bunch of targets. They would choose targets that they wanted to then refocus on with a smaller field of view instrument like the ChemCam laser, or perhaps do a zoomed in image with multiple filter wheels. And then they would score these different targets, and then they would build an instrument sequence that would then fire the laser at that target. That's very inefficient because you have to have the ground in the loop, and you only can do that either near the end of the sol, or at least you can't move after you do that. Now there's advanced software on board MSL and on board MER that automates that entire pipeline. So they can drop in this large block, and the rover will take the wide field of view image. It will score the targets according to the specific science criteria that the science team has chosen for that day, and they can command it to say, image or hit any targets that are over a certain threshold, hit the top 3 targets. There's quite a bit of flexibility in that. It finds the targets, and then it determines the target position, and very importantly, it checks to make sure that this target is far enough away from the rover, because it's a very bad day if you shoot yourself with the laser. And then it goes and takes these measurements, okay? And this technique is so effective that it's resulted in a significant uptick in the number of measurements taken by the ChemCam instrument. So this is a fantastic way to more effectively do science. And the next rover that NASA is sending to Mars, the M2020 rover, is going to have even more sophisticated autonomous targeting capabilities for multiple remote sensing instruments. It will have the ability to target relative to features that it either detects or are specified from the ground. So you can say things like, find that vein over there and take a set of measurements across that vein. and the software is smart enough to find the vein and image and take those measurements relative to that vein. Now, I myself, I'm a scheduling person, not a machine learning person. So what I'm most excited about for the Mars 2020 mission is that for the first time, there will be an autonomous scheduling capability on board that Mars rover. And this is a very important part of the mission because it's very hard to predict how things are going to go on these surface missions because they are robotic. And so this is a simulation of one sol type, which is a medium drive, and then what happens here is the drive finishes early. And so there's a chance that the rover can decide for itself to adjust the measurements that are at the end of the drive. So it could add more measurements, it could do what's called inflate a switch group. Maybe they thought they only had time for a 2x2 raster, but they could grow that to a 3x3 raster, or it could move the instrument observation in order to place it closer to what we call the no heat window. So it takes less energy to heat up the instrument, and it'll save energy. All of these things allow the rover to be significantly more productive, which is very important for these NASA missions. And how does that scheduler work? It works by a variant of the timeline scheduling that I talked about before. So this is actually the scheduler placing these different observations. Those fields that you saw filtering across down here are in fact the constraint windows, which are the valid times that that activity can fit for various types of constraints. So power availability, is the rover on or is the rover asleep? Is the illumination correct? And the all-important energy timeline here, which unfortunately is so thin that it's very hard to see. And right here is the minimum energy for the day. That's very important that not violate the minimum state of charge constraint, as well as there's an end handover state of charge target. So all of those things are managed by the onboard scheduler. So it's not just rovers that we use these techniques for. Since I'm here in Europe, I have to say I had the fantastic privilege of working with the European Space Agency on the Rosetta mission, where we deployed activity scheduling technologies to help schedule very complex observation constraints for the Rosetta orbiter. This was a collaboration with the ISAC Center near Madrid. And we also deployed a system to manage the data buffers. This is a very complex problem. You have all this data coming down. You have certain deadlines where you want to bring data down and you don't want to overflow any of the data buffers. These here are showing where the data is very close to the peak of the data buffers. It's a 300 variable decision problem on a 1-month basis, and it's very challenging to solve. And so we were able to deploy AI technology to solve this, not only solve this problem, but allow the engineers to play what-if games with this kinds of analysis. So this kind of scheduling technology is used all over the space enterprises. The Deep Space Network antennas that NASA uses to communicate with everything beyond Earth orbit has been using this scheduling technology for mid-range scheduling for quite some time now. That's most recently it was deployed into near real-time scheduling, and very recently they perform what's called link complexity scheduling. What that means is for every track, they have a model of when it requires the operator attention. Is it a very complicated track? Is it not a very complicated track? So they can balance out the operator workload across these different tracks and schedule them so that they're all not piled up at the same point in time. This actually enables more efficient staffing of the complexes, as well as the follow the sun regime, where now the complexes are operated by one team that shifts to follow the natural workday between Canberra, Madrid, and Goldstone, California. But we don't actually have to go to Mars in order to improve Mars science. This is a fantastic project by Kiri Wagstaff called the Mars Target Encyclopedia. And what they do is they use text analysis and machine learning to analyze correlations between different elements and relationships in Mars science. So they find elements, minerals, targets, and they learn correlations by analyzing thousands of papers from LPSC that classify the strength between targets and elements or targets and minerals. And then when somebody wants to go and look at Mars data and they type in something like hematite, which is a mineral that's very interesting to scientists because it forms in the presence of water, they can immediately be driven to all of the target sites where their colleagues have referenced hematite in papers, in the literature, and they know that these are scenes that they should probably be interested in go look at as well. So this is a way that we're helping the scientists on the ground be more efficient in their scholarly works. So machine learning has unbounded applications in big data and dealing with large amounts of data. As an example, there's this system called the Intermediate Palomar Transient Factory. And this analyzes data every night from the Palomar telescope, which is roughly between Los Angeles and San Diego. And using the best available techniques of computer vision, statistics, and pattern recognition, they would get about 10 to the third alerts per night. And these could be like a point transient, which is a potential supernova, which is very important to detect early on so you can get this early onset data. Or it could be a streaking transient, which could be a meteorite or, not very likely, discovery of a new planet or something like that. And so using machine learning techniques trained on the supervised classifications from prior data, they're able to drive this 10 to the third cases down to the top 50 cases that the scientists are most interested in. That's a small enough number that they can review all of them. There's also a separate holdback set that's used to correct for potential bias in the machine learning that they also look at that are selected randomly. So this is work by Uma Rapapagada and her team. They're also using this same technique of triaging large amounts of data using machine learning in fast radio bursts. This is not only in vFaster, but also the AKSAP survey and several other surveys. And again, these are different radio science bursts that you might have seen in the popular media. That's because the popular media likes to talk about how these could be signs of alien civilization that was just waiting to be discovered. While that might be the most interesting explanation for this data, I'm not sure it's the most likely. But in any case, they are drowning in this data. Just from vFaster, they would get, again, using signal processing and statistics and pattern recognition, about 10 to the fifth hits per 24 hours. Once again, with the continuous quality control and retraining and a closed-loop machine learning, they're able to get this down to the top 50 hits per 24 hours. Again, a manageable number that they can all look at, the scientists can focus on. And this wouldn't be an AI talk without some reference to deep learning. This is some very late-breaking work by Brian Bowie and David Thompson, and this is using data from the AVERS-NG airborne platform. Previously, they used a standard match filter in order to detect fugitive methane emissions. They fly over a site and they can determine if there's a leaky pipeline immediately or a fracking site that's leaking. They applied a secondary stage here of a convolutional neural network or deep learning, and they're able to drive their sensitivity significantly higher and detect even smaller emissions. And this is something that's being done routinely now in the airborne platform. We'd like to do this someday in space. I want to emphasize that there's, even though you've heard a lot about work going on at JPL, there's a great deal of outstanding work going on all around the world. I'm just going to mention a few of those. At the Space Telescope Science Institute, they've been using automated scheduling on the ground for quite some time. Since 1993, Spike and Trans have been used to process pretty much every HST observation that's ever been done. This shows the long-term scheduling profiling done by Spike. This is the detailed automated sequence generation from Trans. Spike is an incredible system. It's been used to schedule all 4 of the great observatories, NASA's great observatories, as well as Subaru and Fuse, and it's being adapted right now for JWST. Mark Giuliano is the point of contact for that work at STSCI. NASA Ames has a long history of doing outstanding work in artificial intelligence. Just some of the things that I want to highlight: the LADI activity scheduling system by John Brzezina, used to operate that mission, and then work on the inductive monitoring system used to monitor various ISS subsystems and to do anomaly detection there, work by David Iverson at NASA Ames. And of course, ESA has a long history also in deployed AI systems. MEXAR has been used in data downlink management for Mars Express for quite some time. And then novelty detection in work by Alessandro Donati's team, along with Jose Martin Harris at ESA ESOC, has been used in anomaly detection for XMM Newton in other missions. So now I'm going to talk a little bit about the future. What are some crazy things that we would like to do in the future, some not so crazy things, and what we see as growing trends in the use of AI in space? Well, one of the things that I saw up close working on Rosetta is this challenge of pre-sequencing when you go to a dynamic environment. So we had to plan the science operations of Rosetta 2, 4, even as much as 8 weeks in advance. And so we barely knew where the comet was 8 weeks in advance, much less for dynamic phenomena such as plumes. And so when we could take wide field of view images of the entire comet, we couldn't use that information to target very narrow field of view instruments like the microwave instrument on the Rosetta orbiter, MIRO, which could tell us very good compositional information about the plumes and as they evolve over time. Or to target the ALICE instrument, which could also give us great compositional information. What we would really like to do is, for this very faint plume, do a bunch of very fine measurements across that plume to get the detailed information of the evolution of that plume. So we worked with Holger Sierks at the Max Planck Institute, not that far from here, and developed a set of computer vision techniques using active contours to do exactly this. And this is a technique that we would like to fly on a future mission to a comet. So what we do is we actually take a pre-guess from navigation information as the outline of the comet. We adjust that dynamically using the actual images that we've seen, and then we develop what are called a set of gradients going further and further from the nucleus. And we look for peaks in that, and we can actually do that and align the frames from rotation to rotation so that we can identify an individual plume and track it through the sequence. This is exactly the information that we would use to target MIRO or ALICE in the case of Rosetta to take those follow-up measurements. So this is a tremendous demonstration of the unique science that we can do with AI that we cannot do without AI. We have to be able to close those kinds of loops in order to make those kinds of measurements. Another thing that we're seeing increasingly is the infusion of AI into the mission design and mission analysis process. Now, in my lab at JPL, we have almost as much work. About half of our work is for analysis of missions before they're being built. So this is an innovative mission concept called RELIC, where we would fly 128 CubeSats in a lunar lysaceous orbit in order to conduct a sky survey at very low frequency radio to observe distant galaxies. So we would launch this in a single launch, and then we would deploy all of these spacecrafts aboard a single mothership, and we would collect all this radio science data with very simple dipole antennas, send it to the mothership, and then downlink it to Earth. So we want to do this galactic survey, and the question is, how do we construct these orbits? Obviously, if there's 128 spacecraft, there are going to be a lot of different orbit combinations. Well, how does the interferometry work? We have this target that's effectively at infinity, and if we look at the plane that's orthogonal to that, these multiple spacecraft construct all of these baselines that are measurements of this distant signal source. And because the signal source is not changing very rapidly, over the course of days, we can fill out this curve, this plane, of various baselines and various orientations. So distances and orientations are what we care about. We can change all of these orbits in certain specified ways, the inclinations, the spacings, and the size of the orbits, and we can be very clever. We can start with all these small orbits and grow them all incrementally to fill out the small baselines and then fill out the larger baselines. Again, how do we figure out what's the most effective way to do that? We also need to manage the fuel in these spacecraft. As we grow the rings or we change the inclination, that costs fuel. That fuel is mass, and that mass is part of your overall mass budget. Then what we do for all of those orbits is we now measure for all of the configurations how well we fill out the observation curves for all of the celestial sphere. So what does that really look like? It looks like this. So we have 1/2 of this that's being filled out as those orbits that you saw in the first animation, and this is showing how they fill out that curve, and what the scientists want to see is this whole right hemisphere completely full. So for these small baselines, they would be very happy with this. So the goal is to construct out of this vast set of orbits and growths, ones that will fill that observation curve. And that's in fact what we do here. We can actually grow them from 0 spacecraft and start adding spacecraft. We can start with a large number of spacecraft and move down. We can actually simulate losses of spacecraft, figure out which configurations are robust to the loss of spacecraft. We can do forward and backward greedy search. We can even do bidirectional search, where we approach from both directions. We have a target number of spacecraft. We do something like simulated annealing, where we add some more and then we remove some in a greedy fashion. And we can actually do that to optimize this constellation. The quite surprising thing is we were able to find solutions that perform 20% better by this coverage metric than the best human-derived solutions. But we don't consider this a competition between the software and the humans. We think of this as a synergistic team where the person suggests a new formulation of the problem, the computer does a lot of search, that might lead the human to have inspiration as to explore a new area of the search space, thereby using the true smarts of the human orbit designer in conjunction with the brute power of the computer to arrive at the best possible solution. I talked a lot about Mars rovers. We've now seen rovers on the surface of Mars for quite some time. Many of the younger people in the audience don't really know what it's like to not have rovers on Mars since Mars Pathfinder landed, I guess, in 1997. But where have we not gone? We want to go to caves, both on the Moon and Mars. We want to go to caves for 2 reasons. First of all, if we can go to caves on Mars, it'll tell us more about the geological evolution. But also, if we want to send humans to Mars, caves are pre-built radiation shelters. The problem is, once you go in the cave, it's hard to communicate out. So one approach to this is to send multiple rovers in and allow them to coordinate and relay the data out. This is very helpful because now when you have these smaller, cheaper rovers, they might die, as we're going to see here. One of the rovers stops moving, and the multi-agent coordination algorithm needs to recognize that and move on. And so this is using a dynamic zonal allocation method where the rovers allocate areas for different depths inside the cave, and they go further and further in. As they go beyond their relay distance, they start having to sneaker net the data by driving and shuttling back and forth. Eventually, all the rovers will die, and it's a very sad thing to see the last 1 or 2 rovers futilely trying to go all the way in and take measurements and go out. But Mars is a cruel place. What about if we go someplace truly unexplored? How do we bring back the most important data? Well, to do that, we have to go back and study what it really meant to have limited downlink. So when we take a mission now, when we fly a mission to a new planet, we take hundreds, tens, thousands of images, and we take an image, everything we see, every 100 meters, every 10 kilometers, whatever. Well, back in the old days, when Lewis and Clark explored the Pacific Northwest, they went for weeks and months, and all they could bring back was roughly 100 pages of text that they had to write themselves by hand. They didn't even have a camera. They had to draw pictures. And they saw all these things they'd never seen before, different kinds of animals. So what did they do? They classified things into higher level objects. They drew a map with lakes, rivers, and mountains. They didn't draw a picture of every mountain, which is the equivalent of what our space missions do. So if we go to a truly unknown environment where our downlink is very limited, that's exactly what we want to do. So we did an experiment. We had a poor summer intern on a cross-country flight take hundreds of pictures out the side of the airplane. We then applied clustering and metric learning to cluster those images using different kinds of features like texture, albedo, and so on, and then use metric learning to separate those clusters. We then downlink instead examples of the clusters and a map, exactly like you saw with Lewis and Clark. And surprisingly, we have scientists do exactly the same thing, and we get remarkably similar results. We have here some images of lakes, we have some images of clouds, we have some plains here, we have many more clouds up here. And so it turns out this is a very effective way to use downlink. So someday when we go to a completely unknown environment, these are the kinds of techniques we can use to efficiently manage our data. And now I'm just going to spend a little bit of time on a topic that's very near and dear to my heart, which is what's a most laudable goal for all of us in this room to yearn for, to discover life beyond Earth. And obviously, as an AI person, I believe AI is critical to that search. So there's a lot of interest in Europa, as well as other ocean worlds. Why is there this interest? Because they believe that there's a liquid ocean underneath an icy crust here. When I was a kid, the conventional science thinking was you couldn't have life without photosynthesis. But the beautiful thing about science is it knows how to reinvent itself. Scientists discovered these hydrothermal vents at the ocean seafloor. And lo and behold, in the absence of light and no photosynthesis, there was a habitat there that sustained life. There's now elements of the science community that believe that indeed this is how life started on this planet. There's reason to believe that perhaps Europa and perhaps Enceladus may have these hydrothermal vents. So what would we like to do? We would like to go to these planets and investigate these oceans. But that's not an easy endeavor. I apologize for the age of this video. We need to get to Europa. We need to land. We need to penetrate the ice cap, which might be 10 kilometers or more thick. And then, once we penetrated that ice cap, we have a single point of entry, and now we want to explore that ocean. What's the challenge? Well, if you want to explore a significant portion of that ocean, you need to navigate from a single beacon. You need to go out and come back. You need to continuously go out and come back further and further, traveling as many as thousands of kilometers in order to go from the poles to the equator or vice versa. So that might sound like science fiction, but we already have efforts. Whoops, went the wrong way here. We already have efforts trying to study what kinds of AI would it take to conduct such a mission. We had the privilege of participating in a cruise on the icebreaker Polarstern, operated by the Alfred Wegener Institute, very near here, out of Bremerhaven, on an expedition led by Antje Botius of the Alfred Wegener Institute, and also participating Chris German of the Woods Hole Oceanographic Institute, the world-famous hydrothermal vent hunter, Chris German, and Kevin Hand, an eminent astrobiologist. And we were very fortunate to have Andrew Branch, a member of my team, on this expedition. And his goal was to study how this fantastic team of tens of scientists and engineers mapped out the terrain and conducted their search for a hydrothermal vent and explored it. And our goal is to build a set of algorithms based on this technique called nested search, pioneered by Chris German and Mike Jakuba, also at the Woods Hole Oceanographic Institute. And this is a simulation that we have of a hydrothermal vent with this nested search technique. And what it does is it yo-yos, searching for what's called the neutral buoyancy field, where the signal is going to be strongest, and you have the best chance of tracing that back recursively to the source. Not only that, not only do we want to find these sources, we want to detect different science events that we see along the way as we're exploring this terrain, because all of the ocean is not equally interesting. So we actually have projects in collaboration with JPL, Caltech, the Monterey Bay Aquarium Research Institute, the Woods Hole Oceanographic Institute, and Remote Sensing Solutions, where we've deployed large numbers of autonomous vehicles. This is off the coast of Monterey. We have sea gliders, we have Tethys AUVs, we have IVR AUVs, and we use them in a coordinated fashion to track ocean fronts. So we want to actually fly a formation of these vehicles perpendicularly across the ocean front and move as it translates and rotates. And this is what the track of what one of the individual vehicles sees. This is actually, we're plotting here what's called the gradient of spiciness of the water. This is a buoyancy-corrected measurement of the salinity in the water, and the scientists are interested in these shallow gradient fields and then these large disruptions here. And as they evolve over time, both the diurnal cycle, the daily cycle, or over longer periods of time. And so they want to get in one of those features and keep crossing it so they can study its evolution over time. And these are exactly the kinds of techniques that we want to use to do autonomous science, not only on the Earth, but potentially someday on an ocean world. And then the ultimate challenge for AI. There's going to be, well, I should mention that there's going to be sessions on ocean worlds tomorrow. If you're interested in that topic, you should go to those sessions and hear much more about the fantastic and challenging technical challenges that it would require to conduct such a mission. I only talked about the AI aspect of it. There's many huge challenges, like how do you get through the ice cap? How do you have mobility and things like that? There's also great sessions at this conference on the Interstellar Mission. Let's imagine we go to the nearest star, Proxima Centauri. It's a little over 4 light years away. It might take you anywhere between 40 and 100 years to get there. When you get there, you're pretty much on your own. Any guidance that you get is going to have to wait 9 years round-trip light time. So your AI better be good if you want to get good science in that mission. If you want to go to the TRAPPIST-1 system, it's much further, more than twice as far away. There's no way you're going to wait 30 years round-trip light time and joystick that spacecraft. So again, your AI has to be very good if you want to get the best return for your investment. So that's a challenge that all of us who are working in AI and spacecraft systems can really sink our teeth into. And what's a better cause than to try and discover life out there in the universe? So with that, I'd just like to end with a few key points here. AI is already in use to solve problems all over the space enterprise. You've seen it in the ground, you've seen it in flight, you've seen it in astronomy, you've seen it in astrophysics, you've seen it in planetary science, you've seen it in earth science. It's everywhere. However, these represent a tiny, tiny fraction of all of the places where AI can be used to great effectiveness. And it's my job and the job of other people in AI to make sure that all of those problems get attacked. And finally, AI, I believe, is critical for future missions that are going to hunt for life beyond Earth. There's much more further information on this, on all the different projects that I mentioned here, and even some I didn't have time for. I'll make sure that somehow these slides get posted. And I want to end with the Jpl Mantra, which is to dare mighty things. Thank you very much for your time and attention. We have time for a few questions now. Oh yes, we can see how the poll is. Outstanding. Not being a machine learning person, I'm very jazzed to hear people are most excited by autonomous explorers and not big data. Because as you know in AI, particularly in the business world, people now think AI is just machine learning and dealing with large data sets. So this is, I have to confess, this is a trick question. There should be a last answer, which is all of the above. Do we have any questions from the audience? Oh, yes, we have a question here. Do we have the mic? Hi. Up, right there. Ah, what is a plume? There's a great story about the plumes. So There's some great articles which are all the things about comets that scientists thought were different from before the Rosetta mission. So originally people thought, like I did, naturally, that plumes would be caused by solar illumination actually heating up the volatiles on the surface of the comet and then causing this plume. It turns out it's an ion reaction. And this is one of the results, I believe, from the ALICE instruments as well as some of the in situ instruments. There's a photoionization effect that then liberates free electrons, then causes the reaction that causes the outgassing. So the answer is, you'll have to ask the scientists, but it's not what they originally thought. Go ahead.
Okay, thank you for the interesting presentation. So I have a question regarding the capabilities of the exploration and also the data observation. So will AI can detect or investigate the pattern of the earthquake in the future?
If I understood your question, you're asking about can AI detect unexpected events? And
Yeah,
sort of,
an unexpected event.
yes, so that's actually, when I was talking about the unsupervised learning, that's what's key there. So when I first started working with Phil Christensen, the planetary geologist, we were talking about using the Themis instrument on board Mars Odyssey to search for hot lava on the surface of Mars. And he gave me this great quote. Pretty much, as a proxy for the value of a science discovery is how unexpected it was, how implausible it appears to the science community. So one of the fantastic things that we wanted to do with the Mars Odyssey Themis instrument, and then we're hoping to do with the e-Themis instrument on board Europa Clipper, is to take vast amounts of data and search for improbable events. And if you do different kinds of outlier analysis, or in these particular cases, thermal anomalies, we know very well how to detect them, you can actually detect these unexpected events and actually do fantastic science. There's a great story about dust devils, starting with Mars Pathfinder. People wanted to go and look for dust devils, but people said, oh, no, there won't be any dust devils, so we can't waste the rover's time looking for the dust devils. They weren't allowed to look for the dust devils until they accidentally saw them. And then they allowed them to go and hunt for the dust devils. That was actually the genesis of the watch system, which we put on board the Mars Exploration Rover mission. And we could take different movies searching for dust devils, process them on board, know whether we saw any, and ignore the data if we didn't see any. So increasingly, we're going to see this kind of thing where the scientists, as they allow the AI to go further and further, it will just allocate some proportion of the data volume to unexpected or unusual things. Things that the software thinks are surprising. Another question? Yeah? Can we get the mic?
Thank you. I'm June from JAXA. And what do you think is the negative part of AI technique, and how do you overcome that?
Well, I'm an AI person, so you're going to have it fine. You're going to have a hard time getting me to say too many negative things about AI. So AI is a tool. It can be misused, right? So if it's not applied properly, it could hurt your mission. You could have anomalies due to, improper validation of the AI software. You could actually, one of the challenges in the machine learning software that we learned from experience with the VFaster and the IPTF is it's very important to have some proportion of the data unbiased by the AI. Otherwise, when you do your different science measurements and you want to publish papers about the occurrences of different things, you still need to have some randomly sampled data to understand the relationship of the subportion that your AI is pulling out with respect to the rest of the data. And this is important not just for science, this is important for many societal and social impacts of machine learning. There's a very forward-looking EU requirement that any AI algorithms that use decision making, you have to be able to explain that. Explainable AI in machine learning as well as in the scheduling system is a very, very important component of the AI. Okay, other questions? Oh, we have one over here. Oh.
Yeah, I'll have a question. I'm Lorenzo, founder of ICO, Intelligent Space Systems. I was wondering about the validation of AI in space application. Do you think there is a need of changing the methodologies on how we validate space software to validate AI?
Yeah, that's a very hot topic right now. I actually think that the same validation techniques that we use now for conventional software, non-AI software, if your team is very experienced with that software, those techniques extend. Now, the challenge is that the space systems that we keep building get more and more complex with every generation. And an increasing proportion of that complexity is in software, not in hardware. But I think fundamentally those are systems engineering challenges, not software challenges. So pretty much every anomaly I've seen in software systems is because there's a gap between the design of the system and the implementation of the system, and that just happens to be in software. A true software error is something like your compiler doesn't compile right. A systems engineering problem that's manifested in software is, for example, on IAC, when they built the original flight software, they didn't anticipate we would be sending these hundreds of different kinds of messages between two of the processors. They allocated a finite size to the table, and we blew off of that, and we had an anomaly. So that's a systems engineering problem that manifests itself in software or in AI. Now, having said that, as the complexity goes up, there's only one game in town, which is formal methods. And that's because these other methods that people are very common about quoting, things like more extensive testing or evolutionary systems or just data-intensive systems, we don't have those luxuries typically in space systems. All the self-driving car efforts, they have millions of hours of testing for any serious effort. We can't test a Mars rover in an accurate Mars environment for millions of hours before we launch it. So we have to be smarter about it and not just throw larger amounts of testing. So those are some of the challenges. I think we had a question over here. Oh, actually, yes. Let's take some of the questions from the screen. So will IA in space support human decision, or will it replace it? So I'm going to cheat and say yes. So there are many ways that you can support human decision-making, like in the design of the constellations. I firmly believe that that's a problem that should be attacked jointly by the human and the software. And there are, in fact, other cases where you can't even allow the human to see the data. If we have this system at Proxima Centauri or something like that, then all of the inputs to the AI have to go in before or just before we arrive. So that's one of the challenges there. What application, we already talked about validation. What application AI robotics is currently developed on NASA? I'm a little confused by that question. Pretty much all of my talk was on applications in AI that mostly were deployed on robotics at NASA. So maybe we'll take another question from the audience.
Yeah, hello, thank you for the talk.
Sure.
I wanted to ask, do you think AI is ripe already to support autonomous asteroid mining, or do we have to wait a couple of years for that future to come?
So the question was, do I think that AI is primed to support autonomous mining of asteroids? That's a question that, in my opinion, can't really be answered because it's wrapped up in a lot of systems engineering questions. So AI is a tool that can be applied to many problems. It's a tool that can be applied to autonomous mining operations. In fact, if you look at terrestrial mine operations, there's a lot of repetitive operations that are already automated. So some of the movement of large amounts of debris, it's basically done by the most benign self-driving truck application that you might imagine, because they don't have people running across and cars doing crazy things. So AI can certainly contribute a lot to that. But I think the overall question of can it be a key factor in asteroid mining and making that possible, it's a tool. It's just one piece of the overall puzzle, and there are many significant challenges in robotics, propulsion. But having said that, there's a lot of exciting opportunities there, particularly if you like to go off on that fringe front and think about 3D printing using in situ resources, and you can go down that whole path of self-replicating robots and robotic colonization.
Thank you.
Other questions? Yes? We have a question up front here. And then I understand that I'm keeping people from dinner, so people can feel free to trickle out as people are. I'm not offended.
Thank you for the talk. I'm Sergio from London, and my question refers to human space exploration. How do you think AI will play a role in it, in addition to robotic explorations as discussed?
Yeah, so I think AI is essential to human exploration in two different ways. So right now, a lot of the things that the astronauts do are micromanaged by the fact that mission control is a very close in light time delay and has a very large bandwidth of data. For example, you would be shocked to know how much time and energy the astronauts spend in inventorying, in unpacking, in packing things. So one important way that AI can be used is to create intelligent assistants so that the astronauts can spend their time on the true challenging intellectual tasks that only the astronauts can do. The second thing is in decision support. There's a lot of interest in taking the voluminous amount of procedures and documentation. You know, in the manned program, they love their procedures, and actually allowing them to access it and track it in a more intelligent fashion, again in decision support, to make sure that the procedures get implemented properly. So those are just two of the ways in which I see AI being a very important factor in the human spaceflight program. Bernard?
Thanks very much, Steve, for your lecture, also for integrating example from the ESA side. And I'm very happy that we proposed you for this lecture. I have a question maybe from a young professional point of view. So if I'm starting in the business, so do I have to invest and also learn some of this AI technique to integrate them in my daily work, or will it be specialized for a few? And are there really career prospects for young professionals to specialize on AI, so beyond terrestrial application, really on some of this space application?
So being an AI person, it would be quite surprising if I didn't encourage young people to go into AI. I believe AI is one of these immense growth fields of the future. The challenge is that you need to actually immerse yourself in it and learn a lot about it. Right now, it's very trendy to have AI technicians. They know how to download TensorFlow, run it, and then they don't really understand at a very deep conceptual level why the system works, although there's a lot of criticism of deep learning just in general that it's not very science-like. They don't understand why it works for particular problems and doesn't work for other problems. But I have faith there's a lot of smart people who are working on those problems, and we will get better and better at that. But I would say that now there's quite a bit of diversity in AI. So I myself am from the model-based AI side, have worked in scheduling systems for decades. There's also the data-intensive side, the data science side. There's not that much cross-fertilization between those different areas, although there is certainly some. So I think it is important to specialize. That doesn't mean that you can't change, just like, you know, I've always been fascinated by economics, so then I went and dabbled in, you know, market clearing mechanisms for resource allocation. So there's always chances for enterprising people to change their fields, but I really believe that AI, not just for space, is a tremendous growth opportunity. It's going to be revolutionizing so many different parts of our lives. And the world is changing in so many incredible ways. I have these young kids in my lab that I enjoy joking with and telling them, you know, there was a time when in order to get money out of your bank account, you had to go and wait in line and talk to somebody. And they say, what? And then I also tell them, there was a time when you had to read this piece of paper to figure out where you were. You didn't just pull out your smartphone and it told you exactly where you were and where you could catch the subway. And then if I really want to get them disturbed, I tell them, there was a time when you picked up a phone and you talked to a human and told them who you wanted to talk to, and somebody else was plugging things in. That's when it gets really troublesome. Other questions?
Thank you for your very interesting talk. I have a question. How creative is AI? Meaning, would AI have landed Captain Sullenberger's plane in a river, or would it just have said, it's a river, you can't land a plane there? Meaning this could work on Mars in similar situations.
Yeah, so that's a very good question. So the question is, how truly creative is AI? Can it really sort of innovate beyond what it's been sort of pre-programmed to do? So I have an interesting story to tell about that. So all of the scheduling systems that I've worked on, generally speaking, I can predict very well how they're going to perform, which is a very good thing in the space industry. We don't like surprises. However, when I have users, science users or other operations people, they're constantly surprised by what the software does. They say, oh my goodness, it figured out it had to downlink all that data. How did it know that? And of course I know it's constantly analyzing that, and it knows these different constraints, it knows how to search those solution spaces. So I really believe that creativity, curiosity, different things like that are in the eye of the beholder. But that's just my personal philosophy. I think just as if you took people from 50, 70 years ago, they would be surprised to see us booking our own airplane flights, and sitting back in the car and letting the car drive itself, and different things like that, and have it rebook our tickets on the fly. Software rebooks us whenever there's a delay. Just as they would say, oh my God, how could software do that? 20 years from now, we'll be looking at same kinds of things, and people will say, oh, of course. So this creativity boundary, it's in the eye of the beholder, and it's a moving target. I think that one day we'll look up and the software will be doing surprising things. Whether or not anybody calls it creative, that's something more for philosophers to worry about. Okay, maybe one more question and then we'll, yes?
Thank you for your excellent talk. I have two questions. You offer many aspects of the use of AI. What's the key point of the development of the AI in the space exploration, do you think? And as the AI always need a big data.
Okay, we'll take the first question before I forget it. So one of the key lessons that we learned in my group is to always focus on the value proposition. And I've also been involved in 3 startup companies. And people at the startup companies always said, oh, this must be very different from your NASA job. No, it's actually the same thing. You're always focused on what's the status quo, what's the value proposition, how are you improving things, how are you making things harder, how are you making things better. I've also worked with venture capitalists, and from the business development side, people always ask, what is the pain point you're solving, and what is the barrier to entry? By focusing on these questions, I think you will find the true problems where AI can provide value. It's not everywhere. It's a tool. The other trick that we've done is we are very embedded with the user. In my lab, which is about 25 people right now, and by the way, we're hiring for any of you aspiring AI people out there that are interested. In my team, we have a large number of people who have worked operations. I've worked Rosetta, I've worked Earth Observing 1, I will be working on Mars 2020 operations. We are embedded in the operations team. We know what their challenges are. We don't propose crazy things because in some sense we know our customers, in some cases we are our customers. So we also have worked with the end users, the scientists. We constantly are trying to understand their motivations. What are the science? What are the value propositions? What are the use cases where we can be successful? And so that's something that I would encourage everybody to do. Okay.
Okay. The second question is, between the applications on the Earth and on orbit, which do you think is we can do first?
Between Earth and what was?
Yeah. As the AI always needs big data, so which one do you think is the more?
No, I don't think AI needs big data. I think data-intensive AI needs big data, and I think model-intensive AI needs good models. So model-intensive AI is just programming in a different language. So when we build up our activity dictionary and our resource models and everything, that's just programming. And when I go to the AI conferences and people say, oh, wow, you're so successful, and I say, that's because endlessly our competition on my heels is some graduate student who wants to write a bunch of Perl scripts or Python program to do the science planning. Because I can't tell you how many times I've gone into some science PI's office and he said, oh, that postdoc over there, he has an idea. He's going to write a Python program that's going to generate all these observations. And it's like, So I live in perpetual fear of that being my competition. And believe me, I'm not helped by the fact that everybody knows Python now, and it's much easier to program. So thank you again, everybody. If other people would like to ask questions, please feel free to come up or catch me during the remainder of the conference. Thank you very much.